So for the approximately 100 in attendance and the handful of people who might be watching the video, let's get ready for the finale here. Okay, so missing data, what is it? How do you handle it? And how do you make a living out of analyzing these data? All right. So here's the preamble. It speaks for itself. You want to be able to analyze all available data. That's going to be a key phrase. All available data should be used, even if they're only observed at one time point. And you want to minimize the biases in the three aspects of analysis: estimate, standard errors, and test the model fit. And we're going to make a distinction between MCAR, MAR, and non-ignorable. And sometimes non-ignorable missing is called NMAR. N as in Nancy, M as in Mary, A-R. NMAR, yes. So missing completely at random, MCAR, is self-explanatory. Variables totally missing by chance, usually only accomplished by having a design that says that it is missing by chance. Namely, for instance, giving different randomly divided groups of people different test forms, like you do in education testing. Maybe multiple cohorts, assuming a single population with that missing data pattern is an MCAR feature, but maybe not. MAR, the greatest misnomer of statistics, missing at random, which should be interpreted as missing extremely selectively. Missingness related to observed variables, so you do allow missingness to be related to variables that are observed, but you don't allow them to be related to variables that are not observed. That can be used. The feature, here's another design suggestion. Given that we now are at the end of this session are going to be able to know what MAR technology is and how to handle it, we can actually design our studies. For instance, think about a study, behavioral science study, where you have a screen, a test or some measurement instrument given to people, and depending on the outcome of that screen, you follow the people. Then you can draw an inference back to the full population who took the screen if you do analysis using MAR. There's certainly missingness for those who were in the follow-up for those who were not selected by the screen, but the missingness is completely explained by the screening instrument values. So that's an example of a missing by design that follows MAR. Then the worst case, the non-ignorable case, which is probably the most common case, missingness related to variables that would have been observed. So missingness related to latent variables is the common term, really. And the latent variables could be continuous or categorical. So we cover both of those aspects of the latent variable framework. So for instance, my favorite example is you have a survey and you ask about health status, and the person comes and knocks on the door to ask about the health status, and the person doesn't open the door because he's sick. So the person's value exists, the level of sickness, and it determines the missingness. That is then non-ignorable, and it's harder to work with. But we're going to present you with some techniques for non-ignorable modeling. Most of the statistical software draws on MAR, which is a much more useful assumption or way of proceeding than MCAR, certainly. So let's take a look at a couple of... is my sound going in and out for you? No. Is it? Sound is going in and out. It's okay in the control room, but not in the back of the room. Anyway, while the technicians ponder that, let's go forward, slide 134. So let's just state some facts here. And here's the classic book that you should have on your bookshelf, Little and Rubin's second edition of their missing data book. A little bit on the statistical side, but not too bad. I'll give you more applied references later on, for those who are interested in more applied references. Estimation using a listwise deleted sample. Listwise deletion, you know, you only use those who have no missing data on any of the variables that you analyze. When MCAR is true, then that's fine in the sense that the parameter estimates and standard errors are consistent, that is, without flaws, except that the estimates are not efficient, which means that they have unnecessarily large standard errors. Unnecessarily large standard errors. And that's because listwise deletion tends to reduce the sample size. So you throw away a lot of observations that have missing data for some of the variables. You reduce the sample size. When MAR is true, but MCAR is not, so you have missingness related to observed variables, for which MCAR would not be true, the parameter estimates and standard errors are not consistent when you use a listwise deleted sample. So listwise deletion is harmful when the more common situation of MR being true but not MCAR. What we're going to focus on is maximum likelihood estimation using all available data. And when MCAR or MAR, or MCAR or only MAR is true, parameter estimates and standard errors are okay. So this is the approach that we're going to take, and we're going to refer to this as ML estimation under MAR. ML estimation under MAR, which comes down to using all available data. So we're going to stay in the maximum likelihood framework, the frequentist framework of statistics, but we're also going to point out the alternative framework of Bayesian estimation, talk about imputation. In the olden days, imputation could mean that instead of a person's missing value on a variable, you took the mean, you inserted the mean for that person, mean using the people who had observations on that variable, and more sophisticated version is regression imputation. But that's not a good technique. It has its problems, and the more modern imputation technique is so-called multiple imputation. It's a Bayesian approach where you create several data sets, and where the missing data is filled in several different ways, differently across those data sets. So you have like 10 data sets at the end, for which you then do 10 analyses and summarize the results of that. That's a multiple imputation approach, which is very popular these days, and programs exist for that. Mplus does not do that yet. And it is, in large samples at least, very similar to ML under MAR. And then pattern mixture modeling is a technique for non-ignorable missingness that we're going to talk about quite a lot here in the next block, in this block. In Mplus, you also have weighted least squares, which is particularly used for categorical outcomes and censored outcomes. And that's not a full information technique like maximum likelihood. It's not an efficient estimator. It's a simplified way of analyzing your model using only first and second order moments. And that means univariate and bivariate proportions for categorical variables. And by that simplification, you lose the ML properties of MAR. You can't do MAR modeling because then you would not be able to have as simple of an estimator. So when there's no covariates in the model, it's actually MCAR that must hold. It's basically a pairwise present approach. When covariates are in the model, it allows MAR with respect to the covariates, in the sense that missingness can be a function of the covariates. But missingness cannot be a function of other dependent variables. So it's not the best method to deal with missing data for, say, growth modeling, where early Y observations are predictive of missingness at later time points. Missingness is a good design technique, like we said. An example that we used in topic 1 was dietary diaries. If you want to predict Y3 here with a variable that has to do with a dietary intake, it may be that that is measured with a lot of error, and for part of the survey you therefore create another measure. Instead, in addition to a survey measure, you have a dietary diary that the person is forced to fill out. So you have two indicators of a latent variable, and therefore you can get rid of the measurement error in the prediction of some health outcome Y3. So there is a design in the sense that here you have the data matrix, the three observed variables, and for part of the sample you observe all three, but for another part of the sample you don't observe Y1, so you have only one indicator, Y2 here. And if the second measure, the Y1 measure, is expensive, maybe that first group of people is a fairly small one. So if you have an expensive measure, you don't have to measure it for everybody. You can just randomly select who should receive both of the measures. And in that case, it is MCAR, missing by design. So that's another design idea that you could use. And of course, in the two cohort growth model here, you can have a situation where one cohort is not measured on 11 and 12, Y11 and 12. So the broken arrows here represent missing, whereas for another cohort you have missing at the early grades. And it's a random selection, so maybe MCAR holds. And working with the missing data techniques, you're able to have a growth model for all of those time points. Our real focus is going to be MAR, missing at random. So let's take an example to see what the advantage is of doing MAR. I'm going to focus on slides 139 and 141. So say that you have a bivariate situation. You have y and you have x, and you're interested in estimating all of the parameters for y and x. So you have two means, two variances, and one covariance. 5 parameters, right? If you look at the data matrix then at the bottom of slide 139, you have columns being x, first column x, second column y, and then you have the first set of people are those who have observations on both x and y. It's the complete data group, and part of the sample then has observation on x but missing on y. So if you did listwise deletion, you would work with a sample here at the top and throw away the people at the bottom, even though they had observed data on x. And you might think that the missingness is a function of x, in the sense that when x tends to be low, below this wobbly line, when x tends to be low, you tend to have missingness on y. So when so n sub L is a sample size for those who are low on x. So missingness is a function of x, and x and y are related to each other. How does MAR estimate the parameters of this bivariate distribution? Well, just to get to the bottom line right away before I wear you out, it pays to use all available data. That box of data, that box of data, and the box of data down here that has observations on X, but not on Y. And the important point here is that the people who have data only on X and not on Y, those people down there in the leftmost box of the data matrix do contribute to the estimation of parameters related to Y. They will improve the estimation of the Y mean and improve the estimation of the Y variance. Only have observations on X. That seems impossible, right? But it's logical in the sense that X is correlated with Y. So of course X carries some kind of information about what Y would have been, right? That is the basic idea of MAR using all available data. The people who have partial data, even the people who have no data on Y, contribute to the estimation of the parameters for the Y. That's all you need to know. Now you can take a nap after lunch, and I'll wake you up when we come to pattern mixture. Then with that as a starting point, I will confuse you with some formulas. So let's consider the regression of Y on X. That's standard linear regression. It seems so simple now compared to all the other fancy work. Estimated as usual. You have the alpha estimate, intercept, and the beta. The covariance divided by variance here is the key estimate, and the residual variance. For this data set on slide 139, with missing data on Y partially, you can estimate the parameters in the regression using the listwise present, the complete data group. So these are the complete data statistics that we're talking about. The interesting thing is that the ML estimates of the mean and variance of Y, ML under MAR, can be seen as an adjustment of the estimates of mean and variance, this is mean and variance of Y, that you get from listwise deletion and those that you get from MAR in the following way. So let's look at the mean of Y at the bottom of slide 141. I wish you could scoot it up, but that was in the older days. So the mean estimate of the mean of Y is Y bar, the mean of Y for those who have complete data. So the mean of Y coming from these people here, this box. That's the listwise estimate plus an adjustment. So ML under MAR is not satisfied with using only the present people mean for Y, but it has this correction term, which has to do with the regression slope between Y and X, beta, and the overall mean estimate for X minus the sample mean for those complete data people. So the mu hat for X is based on everyone minus the mean for X bar here for these people. And if you look carefully at this, you will see that this adjustment is either positive or negative depending on whether the overall mean is higher or lower than the selected mean. We won't go into those details right now. We have more important things to do. The main point is that maximum likelihood estimate under MAR uses not only the Y mean in the sample of complete data, but also uses information on the estimate of mean of X for everybody, which obviously will use the data down here. So it's an adjustment. So there are a few cases where the maximum likelihood estimates can actually be written out explicitly, otherwise with iterations mostly. But it turns out that this shows very clearly what goes on. Similarly, the residual variance, maximum likelihood estimate, is the residual variance from the complete data people plus an adjustment term, depending on it's upwards adjusting or downwards adjusting depending on the difference between these two variance expressions. So the program automatically iterates its way to these maximum likelihood estimates of the mean and variance of y, but conceptually and algebraically, it turns out to have that relationship. So it's pretty neat that the program actually knows how to do that and adjust in the right direction, increasing or decreasing the listwise present estimates. So that's all going on behind the scenes in the multivariate setting with any kind of model that you want to use, be it growth models, factor models, SEM, or latent class models, goes on everywhere. Now, slide 142, we're saying this ML under MAR approach is what's the default in most computer programs. Certainly, it's a default in Mplus. Actually, before version 5, listwise deletion used to be the default. You had to say type equals missing to actually get ML under MAR. But we thought that was so old-fashioned that in Mplus version 5, we switched to having that as a default. So you don't have to say type equals missing anymore. All you have to do is say what the missing data identifier is. So, but the quality of the estimation under MAR, which is the same thing as using all available data, is depending on whether or not missingness can be said to be predicted by observed variables, whether missingness can be predicted by variables that have no missingness. And that then, I would say that you would use MAR no matter what, even if you didn't fully believe in its assumptions. But it can be made more plausible when the model includes covariates that actually influence missing data. The analysis is more plausible the better covariates you have that has to do with the missing data. You know, missing data could be due to the person's education, SES, or all kinds of personality and demographic characteristics. So you could imagine including more covariates in the model to make the missingness assumption more plausible and therefore reduce any biases in the estimates. But the problem is that sometimes correlates or missing data may not have a quote-unquote causal role in the model that is not influencing the dependent variables in the substantive sense, but only influencing the missing data. And then if you include them as covariates, they can bias the model parameter estimation, because you include the variables that shouldn't be in there from a substantive point of view. You're just including them because they predict missingness. Two approaches to deal with the inclusion of correlates or missing data in the proper way are multiple imputation and maximum likelihood modeling. Multiple imputation based analysis, there's a book by Joe Schaefer, 1997, very good book. Works with two different sets of observed variables. One, a set of variables used for the imputation model, and another for the analysis model. So you may have more variables, observed variables, used in the imputation model. Any variable that is correlated with missing data, that is a correlate of missing data, plus the analysis model variables may be included in the imputation model to impute the data, the missing data, whereas then a reduced set of variables is used in the analysis model. So that's very often used in imputation programs like Schaefer's norm program. Now, what do you do in the ML context? Well, you could do something similar there. You can include these missing data correlates. You don't have an imputation model and an analysis model. You only have an analysis model. But you can include these missing data correlates not as X variables, not as covariate, but as Y variables, which are freely correlated with all other observed variables in the model. So if you include these missing data correlates that have no causal role in the model as y variables freely correlated with all observed variables, you're doing fine. You're doing essentially the same thing as the multiple imputation approach. And there's a recent overview of these techniques by Schaefer and John Graham in Psychomethods 2002. You have the reference in the back, where you can read about that. And Mplus version 5.1 now actually automates this for you. There's an automation of this in Mplus, which sets up the right model that includes the missing data correlate variables as y variables, freely correlated, etc., and makes the proper adjustments of model test of fit and degrees of freedom and fit indices that you would otherwise sit and think about a lot because of those extra y variables. And it's done using the option auxiliary equals m. And you will find auxiliary equals m. So that m stands for missing. And I will point you to a page that gives an example of the input. This feature is described in two sources. One is the 5.1 language addendum, which sits on the Mplus website. On the Mplus website, you have a section where you have the user's guide. And there you also have the user's guide language addendum and the user's guide example addendum. That's one source that describes this. And then you can go to Mplus Web Talks. You have the link on the home page. And listen to the talk about missing data correlates that I have recorded. You have the handout pages for that in your handout here, but I'm going to skip over those pages and let you listen to that talk instead. Let me just say a word about missing on x's. Slide 143. This is a little bit related to what we talked about yesterday on different metrics of the log likelihood. Regular modeling concerns the conditional distribution of y given x. Like in regression analysis, we don't specify a model for x. It's totally unrestricted for the covariates. This is fine if there's no missing on x, in which considering y given x gives the same estimates as considering the joint distribution. But on slide 144, with missing on x, if you want to not delete, what Mplus does is delete people that are missing on x unless you make the additional assumption of normality for the x, in which case you can bring the x's into the model and model both the y given x and the x distribution. So missing data handling on x relies on an assumption of the distribution of x and typically normality. So I'm saying that if you are missing on x and want to not throw out people who have missing on x, then you need to augment your model with an assumption about the x's. So it's an expanded model that makes stronger assumptions compared to the model that we usually work with. And you can turn the x's, you can do that, bring the x's into the model by turning x's into y's, for instance, by just mentioning the x variable variances. Then they become part of the model. Just an aside. Here are some technical pages that those of you who are statisticians can enjoy. Nice likelihood expansions. Let's instead have a application, the AMPS data. So this is alcohol misuse, and 49 schools, 2,600 students. We have longitudinal data and average of 3 items during the past 12 months. How many times did you drink more than you planned to feel sick to your stomach, get very drunk? So this, some of my work has been sponsored by NRAAA, hence the alcohol applications. So we have 4 time points, M over 0, 1, 2, and 3. And here's the input. We have the variable list here, and we're going to use these 4 y variables. And here's the key statement for saying what the missing data symbol is. And that is typically 999 for all variables in my applications, but maybe different in your applications. And that's now with the default of type equals missing, namely MAR under, ML under MAR. You don't have to say type equals missing anymore, but just go straight to the growth model, which is a linear growth with a little twist to it, the free time score at the last time point, and pairwise residual covariation. Here is the output on slide 151 that you get if you ask for patterns. Patterns in the output on slide 150 says that you want missing data pattern information. Now this is really useful to study in longitudinal studies. You really want to look at the details of that. In this case, you have 15 missing data patterns. And X here implies not missing. So when you don't have an X like here, you don't have an X. That means you have missing on M over 3, the last time point. You have missing. This is missing data pattern 2. And then you can go down and see for the missing data pattern frequency that there are 143 people who have dropped out at the last time point. 685 have complete data, that's pattern 1. And pattern 8, for instance, is you're only there for the first time point, but you're never there again, and there are 64 such people. We can take a close look at these patterns as we go further. You also get covariance coverage. So try to figure out what that means. So you have for each variable, you look at the diagonal for each first. If you look at M over 3 again, you see 0.68 here, saying that 68% of the sample have observed information on M over 3. 68% have observed information at the last time point. That's the coverage. 75% for M over 2, 93% for M over 1. M over 0, 46%, which shows the non-wisdom, let me put that diplomatically, by the review committee, saying that we don't want to spend money on a pre-intervention time point. We're only going to give you money for observing half of the sample. So this is actually missing by design. So only half of the sample had a pre-intervention time point. But other than that, the progression from 93 to 75 to 68 represents attrition probably over time. Although there are certainly some patterns where people disappear in the third measure, M over 2, and come back at the last one. But that's pattern 3, 73 people. But it seems like the patterns are the most common are the patterns where when you start missing, you're missing for following time points, so dropout. Pattern 2 is of that kind. Pattern 4, 164 is of that kind. And yeah, that's it. So coverage, you want to look at coverage, and you know, Mplus requires at least 10% coverage. But long before that, are you in trouble? You know, when you have too low of a coverage, You can certainly do the maximum likelihood estimation, but there comes a point where you rely more on your model assumptions behind the missingness handling, like normality, rather than relying on the information in the data. You want most of the information to come from the data. So this is pretty low, 68%, maybe 75% is okay. I don't know. Depends. So here's the growth model. Apparently has only 1 degree of freedom, and you have the estimates here. We're not too interested in them right now, except to say that they are maximum likelihood estimates under MAR. Instead, let's look at this picture, slide 157. If you did listwise deletion, you would analyze only the 685 people, right? They're the ones who have no missingness. But now the total sample is, what was it? Total number of people was almost 3,000, or much larger at least. So the question is, why is the listwise, the estimated growth curves are plotted here, estimated growth curves under this model, using the listwise present sample and using MAR. Why is the MAR line higher? The scale here on the y-axis is bad alcohol behavior. Yeah, so the idea is that those who abuse alcohol more tend to be the ones who drop out. And if you only use those, and if you only use those who are in the sample, the listwise, you will therefore have a lower progression of alcohol abuse. So if you only use a listwise sample, you underestimate the growth curve because you don't get the worst cases of alcohol abusers because they drop out. They're not part of the sample. So that's what you would expect, and the question then if that is a serious difference or not. Now, here on slide 158 starts this missing data correlates using ML section, for which you can write, we have a Mplus web talk to go to instead. I already alluded to it, and all I will do is to say that on slide 167 is an example of using the missing data correlates approach to the LSA data. Here is an input excerpts. It's truncated. We don't have the top of the input as we usually do, but you're now advanced and can follow this anyway. So it's right under the use variable list, use in the model math 7, 8, 9, 10. So it's actually LSA over grades 7 through 10. You have a statement auxiliary, meaning let's bring in missing data correlates, variables that are not part of the model. They're not on the use variable list, but that we think might be related to missingness. So we have auxiliary parenthesis M for missing, and then a whole list of variables. Gender, mother's education, home resource, being expelled from school, having been arrested, Hispanic, black, dropping out of high school, schooling expectations in grade 7, thoughts of dropping out in grade 7, lunch, which is a poverty index on the school level, and quality of teachers. Let's bring in that whole swoop of variables as auxiliaries. And they are those the variables that we add as correlates, y variables tacked on to the other y variables, math scores at the different grades, automatically by the model. And in this case, actually, the model is not a growth model. We just want to do this kind of analysis to get the means for the LSA, to do the plot on the left. And what you see then is, here's a model in itself. This model says that you have free covariances between all of the variables. Free covariances between all of the variables. A totally unrestricted model, not a growth model in this case, totally unrestricted model. And it is a model then that estimates the means freely as well. So it's like a basic analysis, but it's done with a model statement and the auxiliary. Because all I wanted to do, I wanted to answer the simple question, what are the best estimates of the means of these variables? You know, I tried to do, this is a mean plot. This is not a growth model. It's a plot of means that I have just connected. And I thought, boy, estimating means is quite a task to do right. You know, here I have 3 different alternatives, or 4 different alternatives. Listwise is the black boxes. Listwise estimated mean is using the complete data, you know, at all time points to estimate the mean. Again, not a growth model, just estimating the means. What's the other possibility? Well, let's take max n, meaning let's use, and that's a triangle, let's use everybody that has an observation on the math achievement at that grade. So the sample size is going to vary 3,000, 2,000, 2,200, etc. over the different grades. And so that's the maximum available people at any given time point, right? So that bounces up high here, and then down, and then hovering around the listwise deletion line. What about MAR? MAR meaning we analyze all 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, all 6 variables together, including those who have missingness at some time point. Doing maximum likelihood under MAR. That is the diamonds here, the diamonds. And we see that the diamond line for the means is lower than the listwise and the max n. So this would be the more intelligent estimate of the mean of achievement at the different grades. Again, not a growth model, just trying to plot the means in a good way. And then finally, trying to improve on MAR by using MAR and correlates, namely exactly what we have on the right screen, is the circle here, which then shows that we get very close to the MAR estimated means, just a little bit lower at the rightmost in grade 12, when we include the missing data correlates. So in this case, the missing data correlates, well, you can portray it 2 ways. This way, the missing data correlates didn't improve that much on MAR, or another way of saying it, the MAR is not too far off. So, you know, it's not a trivial thing to estimate the means of variables. Here are 4 ways shown. Where the 4th approach, the one with the circles, is done as shown on the right. Not a growth model, but a totally unrestricted model. The variables that are used are the 6, 1, 2, 3, 4, 5, 6 variables are used in the model. But on top of that, we throw in as missing data correlates the auxiliary variables. I think if you don't know what causes missingness, it can be hard to come up with missing data correlates, because the missing data correlates have to fulfill 2 requirements. They have to be strongly correlated with missingness, and they have to be strongly correlated with the variables that we would have observed, variable values that we would have observed. And if you have those kinds of correlates, they're often of causal interest in the model to begin with, and they would have already been included in the model. Now, I've only done this for LSA since it's a new feature. In your data, you might find wonders because of this auxiliary approach. And in any case, you can read about that in Schaefer and Graham's psych methods article and see what you think if you find it useful. But it is a convenient technique, very easy to throw it in. Can be for any model, unrestricted or growth model, and that's all you do. Let's turn to non-ignorable missing data, which I really wanted to have enough time for covering. Because in the past we have ignored non-ignorable missing data. And you don't want to do that. There is a whole literature on non-ignorable missing data, that is missing data that is not MAR, missingness that is dependent on unobserved variables. There are two, just briefly, there are two general approaches into this kind of modeling: selection modeling versus pattern mixture modeling. Statistically, they look at the distribution a little bit differently. But the basic idea is that the data that you observe, the data that we have, is not only data on Y, so to speak, but it's also data on missingness. So you observe your Y variables, but you also observe whether or not you have missingness. And there is another piece of information, therefore, in the data, which is the missingness, or M, here in this notation. And we're going to use instead U for it, for a reason that will become obvious here. Let's say what pattern mixture growth modeling is. It is perhaps one of the more practical approaches to non-ignorable missing data that we currently have. Practical in the sense that it actually is somewhat easy to do and is helpful. It's going to allow for different growth model parameters for different missing data patterns. So we looked at the missing data patterns, say the different dropout patterns. And here we're now going to allow for different model parameters depending on when they dropped out. That's the basic idea. And since we're not interested in a separate growth model for the different missing data patterns, the idea is that at the end, we mix the parameter estimates together over these missing data patterns. So essentially two steps to pattern mixture modeling. And this is a technique that does have an applied literature. I'll point you to that in a second. There's an interesting connection between pattern mixture modeling and latent class modeling. So this is a segue into the November courses at Ann Arbor. Here you have a growth model, Y1 through Y4. But as I said, the data is not really only the values of Y, but information on whether or not you have missing on Y. So these U are binary indicators of missingness or not. U1 designates whether or not you have missing on Y1, and likewise for the other time points. So these U variables, they're binary, and yesterday afternoon we looked at patterns, response patterns for binary outcomes, and we said that there were in principle 2 times 2 times 2 times 2, 16 different patterns. Those are the missing data patterns that we're looking at here. So you can then allow different growth model parameters for different missing data patterns in the pattern mixture modeling. And the way it is typically done is to have a variable, a covariate, indicating the missing data pattern. Covariate indicating the missing data pattern, and then have the covariate influence, say, the growth factors, like a time-invariant covariate influencing the growth factors, where the covariate is a dummy variable, or a set of dummy variables, rather, representing the missing data patterns. That will then allow for different growth factor means. Growth factor means differ across the missing data patterns. So then you estimate the model and mix the parameters over the missing data patterns. And you get presumably a better estimate of the better estimates for the growth model. Now, using dummy variables for the missing data patterns is like having a latent class model. This is a latent class variable, C for U, class variable for the U's. So the different missing data patterns can be represented by latent classes, and the latent class is a covariate for I and S. So it's just a latent class portrayal of the standard pattern mixture model. What we're going to do now, if you have the energy to penetrate this, is to make a connection between classic pattern mixture modeling, MAR, missing data modeling, and the more new and sophisticated approach of latent class pattern mixture modeling. And this was your exercise number 2. I did point out that it was advanced, but if anybody has a solution to tell me about, I'm happy to listen. So we're going to analyze math 7 through 10, not all the way up to 12, but 7 to 10 by pattern mixture analysis in the classic sense, MAR analysis, and latent class pattern mixture analysis. And we have half an hour, so we could do it. Let's look at the missing data pattern that you get from output patterns. And there are 15 missing data patterns here for the 4 grades, 7, 8, 9, 10. X is not missing again. And on the next slide, you have the frequencies. So many people have, I think the total is about 3,000 people. Most people have, or 1,659 people have complete data on all time points. Pattern 2, you drop out at the last time point, 355 are of that case. Pattern 3, you drop out in 9th grade and come back. Not as many people. Pattern 4, you drop out after grade 8. 376 people. On the whole, most of the people are following the attrition patterns. But you have in total 15 patterns. You don't have the pattern of missing on all time points because we're only analyzing the Y variable, so those people have no information to give us. Now, how do you do pattern mixture analysis? Classic pattern mixture analysis in Mplus. Let's consider this slide 176. And now we're going to kick it up a notch and actually bring in latent class thinking. We're going to have a new feature, an option in the variable command. Classes equals C16. Although I think it's, yeah, okay. And that is a mixture, a latent class variable, with 16 categories. And you have a feature in Mplus which, like data 2 part, automatically creates data for you. So if you have these variables, these 4 variables, data missing creates a set of binary indicators in your data set to indicate if it's missing or not. So Mplus adds missing data binary indicators to the variable set. So the names are a variable that you consider, and then binary will be the binary counterparts called U1 through U4. U1 equals missing, U0 is not missing. And then the analysis type is the new mixture approach, type equals mixture, latent class approach, where you have an overall model, which is the growth model with a p-width statement. And now we're going to have a bunch of classes here corresponding to each of the observed missing data patterns. So if you start then with class number 1, we haven't learned how to read these outputs very much detail yet, but whenever you have binary items, you talk this thing, the parameters inside the brackets are no longer intercepts but thresholds, but you can think of it as intercepts in the conceptual sense. And U1 and then $y means that it's one threshold, so one cut point, so a binary variable. Talked about that a bit in topic 2. And fixing the thresholds at high values means that U equals 1, missing has probability 0. So this pattern that you write here corresponds to U0000, which is not missing on any of the time points. So this is the complete data pattern. Now this pattern, the next one, you change plus 15 to minus 15, which says that the probability is 1 for U4 being 1. So it corresponds to the pattern 0001. Observed, 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 and missing at the last time point. And by varying the plus minus 15 here for the thresholds across all of these classes, class 4, 5, 6, etc., you represent all of the possible response patterns. So you come down to 16 here, where you have missing on all time points, and that is going to be, let me not focus on that, but at least yeah, I think that's all we need to say. This is how you do pattern mixture analysis in Mplus. You would have to set up these response patterns. Sometimes you don't allow for all of the patterns, but only use the most frequent patterns. And in this case, it's just a overall mixture analysis. We have with a growth model imposed here. But what the default is in this growth mixture model, this is a growth mixture model actually of a special kind. So it segues into growth mixture modeling in Michigan. The default is that the means of the growth factors, INS, the means of the growth factors vary across the classes by default. So this approach will allow you to do what we talked about as the first step, namely you allow for different growth parameters at for the different missing data patterns. So once again, you have all the missing data patterns represented in U, and then by default in the mixture analysis, that implies that the means of the growth factors, INS, are different across the missing data patterns, which is the hallmark of pattern mixture analysis, taking into account non-ignorable missingness. Let's now turn to the second kind of analysis, MAR. So we know how to do missing at random analysis in Mplus. We've been doing it now for a day and a half. And we still don't know how to do it. No, but we want now to do MAR, but not only analyzing the math achievement variables, but also analyzing the missing data indicators. In fact, you could argue that this is the right way to analyze missing data, a model for both the Y and the U's. But MAR assumes essentially that even though the data is for Y and U, it's okay to only formulate a model for the Y's, ignoring the U's. That is the missing data, the hallmark of the missing data approach, MAR. You can ignore the U part. Pattern mixture modeling brings in the U part. That's how you take into account. If you want to have non-ignorable missing data modeling going, you need to bring in the U's, the missing data U's. So what you do here with them, if you now want to do MAR with use, you can do that, and you should expect the same estimates as if you only analyze the y's. This is high-level stuff. You could probably spend a whole day on it. It's a mixture model with 16 classes again, type equals mixture, a growth model. But lo and behold, there's one little difference. This, if you look at the left, that's pattern mixture analysis on slide 176 rather. And we said that the growth factor means by default vary across all of these classes. That's what pattern mixture modeling should allow. MAR doesn't allow that. MAR postulates equality of the factor means across all of the 16 classes. Equality of the growth factor means across all of these classes represented by the missing data patterns for you. So this single line added to the pattern mixture analysis gives you MAR. This single line. It shouldn't be seen as we really believe that we have equal means across the classes, but we estimate one set of means, right, in MAR. It's a regular growth model, one set of growth factor means, only two means, and we just weigh together the information from the different missing data patterns to estimate those means. So this is an alternative, more complicated way of doing the MAR under ML that we've been doing all along. But it's bringing in the use. Why do we do that? Well, so we get a comparable analysis to the pattern mixture, a comparable log likelihood metric. And then you can also, in the MAR analysis, say what the include mod indices and test which of the missing data patterns violate the equality assumption. You know, in the pattern mixture analysis, we allow the growth factor means to be different across all the missing data patterns, but maybe there's only some of them that really need to be different. And mod indices in the MAR run, where you have the equality of missing data of growth factor means, can tell you for which missing data patterns that equality doesn't hold. So mod indices is very helpful in the MAR. And here you have the MAR results. And actually, modification indices point to the fact, model modification on slide 188, points to the fact that for class 4, for missing data pattern 4, is the I growth in initial status mean has a high modification index with an expected parameter change of 3.7, minus 3.7, saying that the growth factor mean needs to be 4 points lower for that missing data pattern for the model to fit well. That then is going towards a pattern mixture analysis where all patterns are allowed to have different I and S means. But it's just taking giving an indication of whether MAR is not sufficient. Non-ignorable missingness is necessary. To summarize what we've done so far, you have the three approaches. All of them using Y's and U's. So adding the missing data pattern information to the model. So we do our usual MAR analysis, including the U's for MAR, and we do it for pattern mixture, obviously. And we're also going to do a latent class pattern mixture analysis. And we, as usual, we're interested in three things. When we can't rely on chi-square, we go by log likelihood, number of parameters, and the BIC. Low BIC is best. So we see that if you look at the BIC, which is the lowest, it looks like MAR is better than pattern mixture, but the latent class pattern mixture is the best of them all. So it has both a relatively high likelihood and not too many parameters. The problem if you look at it carefully, MAR has minus 38,528 in likelihood. Pattern mixture has minus 38,455. It has a higher, this is a higher likelihood for pattern mixture. But you get that improved likelihood at the expense of 40 more parameters, 67 versus 27. So you throw in a lot more parameters because you have a missing data. We have a growth factor mean for each of these different patterns, and you probably don't need that. So it's 40 more parameters, and therefore, although the likelihood is better for pattern mixture than MAR, the BIC is worse. The latent class pattern mixture, which I haven't told you about yet, it's a parsimonious version of the pattern mixture, which uses only 23 parameters, even less than MAR, but has a better likelihood. So even with fewer parameters, do we get a better likelihood than MAR? That's a clear sign that we are barking up the right tree. We're in a better ballpark of modeling in the LCA pattern mixture than in the MAR. The spirit of latent class pattern mixture is like pattern mixture, but we're not expending as many parameters, and therefore BIC wins for that third model. So what is that third model, and how do you use it? And how do you get that published? Isn't this all too complicated and we should just forget about it? No. There's already one applied paper out there in a psychology journal on this latent class pattern mixture analysis. A guy who I helped along in the analysis, and we both learned a lot, Morgan Lopez, and another person whose name I forget, has a paper, and it's on our website, under papers and missing data modeling. And more papers of this kind are coming down the pipeline, also in statistical journals. So this is the future, folks. If you want to be ahead of the curve, this is the way to go. So I know your head hurts at this point, and we're getting more and more advanced, but this is really, this has practical consequences, and it's really important. Okay, so we take the third approach, the pattern mixture approach, which is in the latent class form, goes down from 16 patterns, 16 classes to only 2 in this case. You can experiment with how many classes you need, but in this case 2 seem to be okay. It's a mixture model, which you will hear more about in November, and it is, we're doing growth modeling, and the use variable list at the top, slide 190, includes not only the math scores, but also the missing data indicators. So again, it's using the full information. And again, just to remind you, under MAR, it's okay to not model the use, only model the math scores, which we've done all day long yesterday. But if you want to take non-ignorable missingness into account, which we are doing by these 2 techniques, not that technique, then you need to include the use. So you use a data missing option in Mplus and a latent class option, and you have the growth model here, and you can plot. You can plot both the means of the growth and the profiles of the missing data patterns. Now it's getting really exciting here. You can just sense it, right? Not. So when you do this missing data modeling of use, you will then have something akin to what we did for categorical variables. You have a frequency table test. You have a frequency table test, and I'll put that on the other slide since it's partly obscured. You have it over here. For those 4 binary missing data indicators, you have a 2-class latent class model, and it fits the data pretty well. Chi-square is relatively small related to the relative to the degrees of freedom, both the Pearson and the likelihood. So 2 classes seem to be enough to explain the frequency table for the missing data pattern. And here is the result of this whole exercise, folks. here I'm using the plot feature series equal a series for the u's, vertical bar, a series for the y's, and I get these two plots. First of all, on the left, let's consider the u's. This is the latent class model with two classes for the missing data pattern outcomes U1, U2, U3, U4. What's on the x-axis? It's grade U1, U2, U3, U4. What's on the y-axis? Don't know, can't read. Says probability of missing. Probability of missing. You are now, folks, looking at the first latent class item profile plot that we'll see a lot of in Michigan. There are a lot of them in Michigan. What does it tell you? Well, there are two classes of people. One class that has a fairly low probability of missing at any of the time points. The well-behaved kids who are there for every test. And then another class up here, which has an increasing chance of missingness. Increasing chance of missingness. And you have the class proportions here. And I think it says something like 74 and 26 or something like that. Who knows? So you get the estimate of the prevalence of these two major missing data classes. So the idea is that you use the class membership as covariate rather than each and every observed missing data pattern that you use in the pattern mixture approach. And then for each of the two latent missing data pattern classes, you get a different growth model in the sense of different I and S means. So the people who tend to not have missingness very much at all over the 4 grades are given a higher estimated intercept and a higher estimated slope. And the people who tend to be the dropout people are, on the whole, having a lower trajectory. And so the feature is that we allow for missing data patterns to have different growth model parameters. And then in the final step of the, let me go back. Pattern mixture growth modeling. On slide 171, we said that we would allow for different growth model parameters for different missing data patterns. We have done that also in the latent class version of the pattern mixture. We allow for different growth model parameters. Now we can weight them together, mix the parameter estimates over the missing data patterns, in this case over the latent classes, which will be some kind of weighted average of these two curves on the left slide. And that result is going to be different than the MAR result. The tack we have taken here in pattern mixture and latent class pattern mixture, again, pattern mixture has one latent class for each pattern, which is the same thing as having observed dummy variable covariates influencing I and S, one for each pattern minus 1. LCA pattern mixture can have fewer number of classes, in this case only 2 classes, influencing the binary response pattern. We saw that this part of the model fits well. 2 classes seem to be enough. And for those 2 classes, we allow the means of the growth factors to be different. So the 2 factors are characterized by these 2 item profiles, giving the interpretation of the 2 classes, the non-missing data people and the people who tend to drop out. And the means for those 2 classes are different. So this dummy variable regression changes the intercept and slope mean, allowing for differences in the parameters. And then the final result is one where you mix the parameter estimates of the missing data patterns to get back to what you're to analysis with the same number of parameters as the MAR analysis. In the LSA data, the story is not that dramatic, but that's probably because we work with IRT smoothing over time. In your data, where the observed variables are not factor score estimates like we work with in LSA, you know, theta hat IRT scores. In your data, non-educational data, I can predict that you find dramatic differences in the growth curves. So I said mixing together. How do you mix together? How do you take that last step? Well, you can do that if you look at slide 194. We've laid it out for you. You have this is the LCA2 class approach, mixture modeling, and the growth model on slide 194. And you label the parameters. You label the variance of I, the variance of S, covariance of I and S, and the class proportion, which is the logit for T1, logit for 1 rather, the proportion of these latent classes on the left. And the means are labeled in the two classes, mean of I1, mean of S2 in class 1, mean of I2, mean of S2 in class 2. And you use the model constraint feature, where you can define a set of new parameters, probability of being in class 1 can be, missing data class 1 can be expressed by the logistic expression, probability of being in class 2 likewise. And then you have the mean, the mixed mean for I, mixing these two, as the sum of the two weighted terms here, the mean for class 1, mean for class 2, weighted by the probabilities P1 and P2. Same for S, and a little bit more complex expressions for the variances. But all handled by model constraint. You just copy this. And maybe you will say, one day, could you put this into the program to make it automatic? And the answer is yes, if you really want to. Certainly, we could do a pattern mixture automatically, setting up all of these different classes. Certainly, we can do the mixing automatically. This is early stage stuff. So this is the mixing over the classes output. And what is the new stuff? The new stuff comes here, slide 201. 201 gives you, these are parameters, the new additional parameters that were not part of the model, but were defined in model constraints as new parameters. So what are they? They are the probabilities of being in the classes. They are the mixed mean for I, 50, and the mixed mean for S, 3.74. So the mixed mean for I, 50.227, sits somewhere in between of these two means. And likewise, the mixed slope is somewhere between this one and this one. Computed by Mplus with its parameter estimates and standard errors and z-value. Same thing for the mixed variance for I, mixed variance for S, mixed covariance for I and S. So I don't know that there's any other program that actually can do this at this point, although tailor-made research programs probably can. And I'm not saying that it's quickly done, but it is doable. And meaning, when it's doable, today, August 2008, it means that shortly it will become automated in a later version. So it will be easier. At least if one finds enough interesting applications where it makes a difference to motivate the time investment in automating it. We talked about automating it. There are many other non-ignorable missingness approaches in the literature. Just to mention the ideas, sometimes missingness on a U can be a function of the Y value that you would have observed. I gave the example of the person being sick behind the door. This is something that statisticians have worked with. Wu and Carroll in the biostat literature. I think this is doable in Mplus. It's not an easy modeling task. There's a book by Sofia Rabbe-Heskech and Anders Skråndal. It's structural equation modeling, latent variable modeling that we referred to in the topic 1 reference list that lays out, discusses this a little bit, and point out that it's not always an easy model to deal with. There is a model that I have actually used in Mplus to try to handle non-ignorable missing data. So it's not pattern mixture, it's a different one. And another idea is that missingness can be a function of the slope. You know, if you have cognitive development, and if it starts going down with a more and more negative slope, that can be predictive of dropout. Person gets old and frail and doesn't want to be part of the study. So when the slope value for a person is particularly low, the missing data probability is particularly high. So again, this is missing data predicted by a latent variable. And this is used quite a lot in HIV research, CD4 count research in biostatistics. This is not just dreaming. This is what people actually work with. But it's high level, so latent variables predicting missingness. For us, it's easy to say in Mplus, U on S. But, you know, there's more to it. You have to be sure that you're doing this well, and it's not straightforward. You can also argue that it's really classes of development that influence missingness. For instance, if you have an alcohol problem outcome here, an escalating class of alcohol abuse may be more prone to missingness. The latent class influences missingness. But again, that's really a topic for the second day, topic 6 in Michigan. Further readings on missing data analysis. The first one, Hedeker and Rose, which I referred to in my exercise number 2, is a pattern mixture applied paper in this multivariate application book. Pretty good book. Don Hedeker writes well. He's done a lot of statistical papers on this too. Little and Rubin again. Here's the Morgan Lopez and Fall Stewart. Again, JCCP taking the methodological lead here, folks. JCCP, that's where the latent class pattern mixture approach is described. Don't want to take anything away from this team, but it's a tricky topic to describe. Well, there are a couple of statements that I don't totally agree with, but on the whole, it's a good description of the technique that I've been talking about here on the left, and done well. Here's an early paper on SEM with missing, not completely at random. Here's a JASA statistical article. And here's the person who probably have a lot to do with influencing non-ignorable missing data modeling using a latent dropout class model, namely the latent class pattern mixture analysis. Roy in biometrics. So this is an emerging field that I want you to be aware of, and you know, if these people could do it, none of them is a statistician by training, not a PhD statistician, you can do it. And they didn't have the advantage of having all these handout notes either, so more power to them. But we wanted something advanced for you, so there you are. This is a good article that you should read if you have missing data, longitudinal data. It doesn't deal with, I think it deals with pattern mixture modeling, but I don't think it includes latent class pattern mixture modeling. But it's a good overview, which takes you through the topic very carefully. So my main aim was to stimulate you to study this topic and know about the different pieces of the topic without necessarily thinking that you would be able to penetrate all of them at this high speed. You could certainly spend a day on missing data as well, but then it would be 9 topics, and I would need an easy chair to sit in. So with that, let's stop and see if we have questions before the cookie break. Yes. No, 15 here for the threshold on slide 178. It's a logit value, and a very high or a very low logit value implies a probability of 1 or 0. So plus 15, logit plus 15 implies a probability of 1. Logit minus 15 implies a probability of 0. Well, actually, it's the opposite here because it's not, it's the negative, it's the thresholds which are the negative of the loadings. So let me rephrase that. A minus 15 for this threshold implies that the probability is 1 that u is equal to 1. Minus 15 threshold, which we're looking at here, implies that the probability that u is equal to 1 is 1. U equals 1 was missing. So minus 15 says that that variable is missing. So we have a 1 for that u. Actually, I should go back one thing. So this is just trivial matters, you know, nomenclature. So here you have the connection. You see the connection here in the comment here. When you have plus 15, the probability is 0 that u is equal to 1. When threshold is plus 15, probability is 0 that u is equal to 1. And u equals 1 is missing. So the probability is 0 that u equals 1, that u is missing. So it's not missing. So anyway, plus 15 not missing, minus 15 missing. Plus 15 not missing, minus 15 missing. That's all it means. Yes?
Go back one more slide. I was noticing that those later patterns were very low frequency, and I was wondering how get the estimate for the growth parameters in this class.
Oh, good point. So we see here that on slide 175, the frequencies of some patterns 11 to 15, which are these patterns here on slide 174, intermittent missingness patterns, are fairly low, which implies that the growth factor means have very few people to draw on, like only one person here. That's a good question. So, and we said that each class estimates 2 class-specific growth factor means, one for I, one for S. So how can you estimate 2 parameters, only one person? And that then creates an almost singular information matrix. But it doesn't matter in terms of the log likelihood. The log likelihood is still a trustworthy quantity, even for a non-identified model. And that's all we used the pattern mixture approach for. But in practice, you may want to, certainly when you have worked with observed covariates in the classic pattern mixture approach, observed covariates for the patterns of missingness, you probably delete these. You don't even work with the small frequency patterns. But here you can. Here you can, because the log likelihood is still okay and can be used for comparison with the MAR and the Latent LCA pattern mixture. Okay, other questions? Yes, in the middle.
I'm just wondering what kind of sample size you need to even consider doing this?
I don't think any different than not doing it. I don't think so. If anything, you're using more information by bringing in the use, so you should do better. It may be harder to, if small samples, it may be harder to assess if a 2-class model instead of a 16-class model fits better. But in terms of getting the parameter estimates, I'm not sure. I guess that's a good practical question to explore in practice. I wouldn't expect difficulties, but I may be wrong. Yes.
Yeah, I was wondering on slide 190 when you decided to
109?
No, 190. When you decided to bring in the two latent classes for the yeah, right there. Did you do that in a separate step where you went through and analyzed just the U's, the patterns in the U's?
Yeah, exactly. Yeah, so you know, it again looks almost like a two-part model, right? The model for y and the model for u here. So I actually, yes, I did an analysis where the ultimate use variables, the variables that used in the model was only this part, and I did a latent class model for it. And then once I was satisfied with that, I did the whole model.
Yeah, so a similar question about the pattern mixing model. I think for the pattern, if we only have one observation, actually it's, you only can identify the intercept. You can identify the slope, right? So in this case, how Mplus handle, it just totally ignore those observations.
What did you say, Lat?
So for the pattern, you only have one observation.
Right. I heard that.
I think when you fit, you can fit the random intercept and the random slope at the same time.
That's right. What happens if you try is that you get a singularity message, singular information matrix, which says the model is not identified. But what I'm saying is that even so, the log likelihood, the maximum log likelihood that you get is trustworthy. It will be the same even if you fixed that, if you didn't try to estimate that extra slope mean that you can't identify. The log likelihood value is still trustworthy. And all we are doing in the pattern mixture here, using all the patterns, is to get the log likelihood value to compare to the other two models.
If you want to collapse several classes, you get a big one, so what are we going to do?
Yeah, exactly. So the question is, well, when you have those small frequency patterns, missing data patterns, you do want to collapse missing data patterns. And in the classic pattern mixture approach, people have to do the collapsing themselves. Subjectively, the latent class analysis collapses the patterns objectively through the model. Basically two patterns in this analysis.
So another question is, have you tried out to use the selection model in the Mplus?
So I have not tried selection modeling. Well, I have tried. I alluded to that here. Let's see. This is a selection model. So this is modeling y and then modeling u given y. So this kind of model I have tried out. And I've actually tried out this model too, and this model. But I'm not finished yet. In fact, I did this like 5 years ago and I put it aside because it took me too long to do it. So I would be happy if somebody picked up on it and tried to explore this.
Yeah, one of my questions is, say if you model drop out. So
yeah.
Basically, you assume if people drop out a priori after all the operations zero, they're missing, right?
Yeah.
So you can really use U1, U4. You can put 1, 1, 0, 0. Because the U4, you definitely know it's going to be 0. So if you put 0 here, when you write down the likelihood, you will put another extra term over there.
Right. Well, here people can come back here. You know, they can be missing early on and then come back. We're not just doing the attrition patterns.
So if we want to know, we know it's attrition. So what are we going to do?
Yeah. Okay. If you really know that it is attrition, then you should model it. So once you have missingness here, you will have missingness here and here. Then the model should have some kind of restriction on it, so that missingness here implies that probability is 1 that you have missingness here and here too. You could do that, I think, by regressing U3 on U2, U4 on U2 with some restrictions. So you can impose that structure if you want to. Yes?
Talked a lot about how ML is a good estimator of missing data. What about in the case where you do have categorical or censored outcomes and you use these squares as attritions in your best options?
Yeah, so the question is, ML is good for missing data analysis, be it using MAR or being pattern mixture analysis. What about weighted least squares? And again, I think I alluded to that missing data handling in weighted least squares, the limited information weighted least squares estimated that we're working with, is not great when missingness is predicted by previous y. If the value of y is particularly high, like escalating class here, high y value means missingness is more likely to be the case for the remaining y's, then weighted least squares is not good. But if missingness is predicted by observed covariates are in the model, then weighted least squares is fine.
But what if it is predicted by otherwise?
Then you have to fall back on ML.
So you would just model it with ML regardless of the fact that your outcome is the same.
Ah, I'm glad you said that. I'm glad you said that. So just to repeat, you would use ML although your outcomes are categorical, was the statement. This is a very common misunderstanding that I hear a lot on SemNet. People think that maximum likelihood means continuous normal variables. No, maximum likelihood is an estimator that can be used for continuous normal outcomes or for categorical outcomes. ML does not mean continuous outcomes. But I'm glad that was spoken because that is such a common misunderstanding, probably because we always talk about ML for continuous outcomes. So ML exists for categorical outcomes. So what we talked about yesterday at the end, growth modeling categorical outcomes, was using mainly maximum likelihood analysis still. Maximum likelihood, just all it requires is a distributional assumption. It could be normal, or it could be Bernoulli, or it can be, which is like binary, or it could be count, Poisson. It just needs a distributional assumption, but ML can handle any kind of outcome. It doesn't mean continuous. All right. Yes.
So slide 167.
167.
So you had mentioned this morning and yesterday that when you try and build complex models, you start from simpler models and work your way up. So if we have missing data and we think it might have an impact on our estimates, do we go, when we build our more complex models, do we go off of this model or off of the model without missing data first? Like if we have this, is there a way to build more complex models off of the missing data model?
So your question is, if you have missing data, which order should you do all of these analyses in?
Basically, yeah.
What do you think, folks? Which order will you choose?
Do it both ways.
Well, there are 5 ways, though. I would certainly start with maximum likelihood under the MAR assumption as the first step. If I had really good ideas about auxiliary variables, I would try this approach. It's very easy to do. Auxiliary missing data correlates approach, and see if there's any difference, if I get any different results. If I really think that there is very selective dropout over time, I probably would do the pattern mixture and the latent class pattern mixture. So if I had a longitudinal data set with missing data in it, with all the money that goes and effort that goes into collecting the data, I would probably do all 4 analysis: MAR, missing data correlates, auxiliary, pattern mixture, and latent class pattern mixture. I would really penetrate the missing data aspect. By the way, for those of you technically interested, there was just a paper that came out. I brought it with me on the plane, so like reading. National Journal of Biostatistics. An INSERM, you know, the French NIMH group. Very nice paper about pattern mixture, latent class analysis, where there's yet another twist to this that I haven't mentioned. I didn't want to blow your fuses. Is that survival analysis is embedded here too. That is, you can model the time to dropping out of the study, bring in the continuous time survival analysis aspect to the missing data handling. It looked like a very nice paper that blends substance and practice with high-level statistics, taking the Roy et al. Latent class pattern mixture modeling a little bit further. There's also a US team, Lin et al. I don't know if you have that in the reference list. It's been using that in the context of dropping out of HIV CD4 count studies. So I sense that this is an emerging area, and practitioners, analysts, people like you are could benefit greatly from. Yeah.
We have two populations. Therefore, this data can be considered from
Like a treatment and control group having different prevalence of missing data. Yeah.
how would we approach the treatment?
Well, so let's say that you have a treatment group and a control group, and you have more dropout in your control group because they don't benefit from the treatment. They get tired of being part of this. I would do a separate analysis first of each of the two groups. And if I cared about the longitudinal data, I would do all of these analyses. And then I would try to do a multiple group analysis or having the treatment control variable as a dummy variable and try to combine the model features from each of the previous analysis somehow. I don't think it should be impossible, certainly. For instance, you may find the missing data profiles be similar but with different prevalence in the treatment and control group. So that would be fairly easy to accommodate in the model. In model it, that's the Yes?
Slide 172, please.
172.
As you keep saying that the missing pattern latent variable regress the growth factors, but we don't see that one in the.
Wait, I couldn't hear the beginning of it.
Right, the missing pattern latent factor CU regressed on the INS.
INS are regressed on CU.
Right.
Yep. Mm-hmm.
We don't see that one in the Mplus program. Is that because?
Yeah, that's a mixture modeling feature that I didn't didn't explain. This is, you actually don't regress I on CU, but the I mean varies across the CU classes, which is exactly the same as if you had actually regressed it on. So you don't see I on CU. You don't notice, we don't say I on CU. But the fact that the mean of I changes as a function of the classes implies the same thing, right? If you actually did dummy variable regression, that's what would happen.